Hello, this is a talk about architecting a SaaS platform for massive scale. My name is Greg Haskins. I'm the co-founder and chief technical officer at Manetu. For some background, I'll tell you a little bit about my company. We're a startup founded in 2019 with a goal of providing a platform that solves the last mile problem of privacy, consent, and incentive management between an organization and their data subjects. This could include customers, employees, donors at a nonprofit, etc. Basically, any type of PII or sensitive data is a candidate. We offer, as a cloud service, the ability to discover, curate, and de-identify PII within the enterprise while automating identity proofing, authentication, DSARs, permitted use consent, and incentive programs. This allows our customers, the enterprise, to increase trust and engagement with their own customers, yield greater value from their data through higher quality curation and auditable consent, and demonstrate a measurable commitment to an important social issue. Building such a system requires an emphasis on privacy, security, and scale in its DNA. We established several first principles to enable both a path to the marketplace in 2020, as well as a foundation to build upon moving forward. This strategy includes leveraging commodity tech that makes building a scalable and robust platform so much easier than it was even as recently as 3 years ago. We strive for cloud-native elements compatible with Kubernetes. This allows us to remain cloud agnostic and deliver a similar experience from dev to prod. We use managed services whenever possible for production. This allows us to focus on our value proposition while maintaining a small operations team. We automate quality gates with CI/CD in every aspect of what we do, and we leverage immutability such as GitOps, Helm charts, and Docker images to ensure our process is repeatable whenever possible. And lastly, I like to adopt the Unix philosophy of do one thing and do it well. We achieve sophistication through composition of simple and solid components, not complexity. This allows us to rapidly iterate and respond to the market. Now, this is more of a architecture slide, but I've included it because it provides a decent overview of our system's composition. We've built a microservice architecture as a core set of services that provide a feature set of our product. This includes account and identity management, data path services, key management, workflow engines, auditing and monitoring, etc. And all this runs on top of an Istio service mesh running on top of Kubernetes. We have a variety of persistence layers. We use Yugabyte for indexed high performance data retrieval, Kafka for reliable messaging, S3 for bulk data object store and disaster recovery, and Vault for security. We also have the ability to integrate with external stores through what we call connectors. We have connectors for things like Salesforce and HubSpot, Active Campaign, Constant Contact, etc. We develop new connectors almost every week. We also have integration with a public blockchain for notarization of our event log. And lastly, we leverage third-party services such as Datadog and Rollbar to help operationalize and monitor the platform. I'm often asked about why we chose a microservice architecture. For me, it comes down to 3 things. Number 1, recognizing that Kubernetes is essentially a data center operating system. Kubernetes has democratized the architectural and operational complexity of fault tolerance, scale, distribution, and load balancing, but only if you embrace its concepts that's actually in a position to assist you. This means things like breaking your application up into fine-grained pods and allows things like load balancers to be defined on the platform so that you don't have to worry about it. Number 2, I want to enable polyglot development. This gives us broader skill set and ecosystem diversity so that we may use the best tool for the job and for our team's skills. It's important not to take this too far though, because each language has some cost in terms of things like our CI templates or libraries for authentication that have to be managed for each new language. So in my experience, 2 to 4 languages tend to be the right mix. And lastly, we like the power to operate both our own code as well as third-party modules alongside each other using the same management infrastructure. So for some context, I just have a screen capture of a recent deployment I made. And on the lower right, we can see basically the state of a Helm chart that was deployed. So we can see the Manetu platform is running alongside some other persistence layers in this development system. Over on the left, we can see there's a variety of Kubernetes pods that were created as part of deploying that chart. And we can see there's some of the names we just saw in the earlier slide on the architecture. One of the things I wanted to point out, though, is that some of the services have multiple instances with a different label, such as EP, GW, CP, EP. We'll get into that in a moment because it's an important part of our design. So one of the patterns that we use in our platform is CQRS, which stands for Command Query Responsibility Segregation. I'm sure many of you are familiar with it. There's a variety of aspects to CQRS. One of the things that I use it for is the strong delineation between the read and write path. Now, not every Manetu microservice uses CQRS, but for the ones that do, we have a mix of what we call personality types, right? So going back to those labels on the previous slide, we have things like gateways and command processor and query processor and event processors that make up the personalities of a given service. The gateway is really designed to kind of be the bridge to the outside world. It implements our authorization policy. It allows commands to come into the system or not, depending on the authorization. The command processor is really the workhorse. This is what takes the commands and acts as the right path to our system. And the query processor is, as the name implies, is what handles our read path. So the queries flow through this component. And lastly, we have the event processor. The event processor is actually very similar to the gateway in the sense that they both submit commands. It's just where it gets its commands from is different. The event processor takes events from our event topic. So in any given service, when we build it, they have similar properties. So there's always one Git repository with one Docker file and one binary that kind of make up this service. And that component is able to run in the various personalities, so gateway or command processor, et cetera. And building them this way allows us to do things like our unit tests can run with an amalgam of all 4 components running together, whereas our integration tests run them apart, et cetera. And it seems to be a pretty good pattern that we've been successful at using. When we deploy one of these components, they each get a dedicated command topic. So the commands for a specific service, like the attribute service or artifact service, they have a dedicated command topic. They also get a dedicated Yugabyte YSQL key space. So they're responsible for the schema and the data path reads and writes to that Yugabyte key space, and no other component outside of this service will touch that. What they do share is a completions topic and an events topic. So that's how our components are kind of wired together. So one of the things I just want to call out was the details of the command processor, since that is kind of the most important component or the most complicated component in the system. Commands come into the system and they may or may not execute, right? So a command can be executed based on the parameters of the command itself, who the caller is, the state of the database at any given point in time. So we'll evaluate the command in that moment and decide whether it can execute. And they've been totally ordered by Kafka on the command topic. So from a write path perspective, we achieve total order through Kafka, and then we implement the policy in the command processor. But we build out scale by doing things like partitioning the Kafka topic and have fine-grained flows coming in to the command bus, as well as fine-grained partitioning into the Yugabyte database. So we can have many command processors executing in parallel, but they each are serialized a very small portion of the overall flow. If a command is successfully executed, typically an event, one or more events are emitted as an output. And we execute all of this inside a Kafka exactly once transaction. So from input topic to output topic to Yugabyte is all encapsulated inside a transaction. And each command is executed as one atomic unit. The pattern we build on top of this is an event processing, or even in some cases an event sourcing pattern, where we can chain these components together. So each individual service, while implementing the personality profile we spoke of internally, can wire together with other services such that one service is consuming the events from a previous service. So an example I'd like to give here is that we have a data subject access request workflow service that can at some point have an approval come in. So when the approval for a correction is processed, that approval will emit an event so that the local database for the workflow engine will update the state to indicate the work item was approved, and it will emit an event which might be consumed downstream by a different service, such as the attribute service, which will enact the change that was requested and approved. And then lastly, once the attribute service processes that attribute change, it will emit an event indicating the attribute had changed, which might be consumed by a third service, such as our analytics engine or our audit engine, to record that that event happened. So we kind of stamp this process out, and that blue event bus is shared by all components. So every component has the opportunity to react to events from any other component and handle them in their domain-specific way. So as kind of a case study here, I was going to focus on one of our services, which is called the attribute service. And you can think of the attribute service as a simple name value pair database. In reality, it's more complex than this. We have to deal with things like privacy and security and usability. So from a usability perspective, we expose the attributes as a resource description framework triple store. We expose a Sparkle v11 compatible query language for components both within our system as well as our customers through API calls. They can invoke the Sparkle queries to query that triple store and get information in or out of the system. But underneath the covers, things are, of course, more complicated. So we have a rich privacy-first model. Inside the system, our triple store is actually carved up into what we call secure vaults. And we have a secure vault per relationship in the system. So if there's two parties in the system, that's one relationship. And basically for every unique relationship, there is a secure vault. And each secure vault has its own unique encryption key. And the what they call IRIs in RDF speak, if you're familiar, the IRIs are de-identified. So the links into our system are obfuscated in a way that you have to have basically a valid access token to the system to be able to decrypt what that link points to. But it's safe to use that link up from outside the system. So you can put these de-identified links in an external store without worrying about leaking PII, but still refer to what the information points to at the appropriate time. So digging in, putting everything together, because of the way we split up all of the services into CQRS components, and then each of those have their sub-personalities, this gives us great flexibility in terms of leveraging all of the things like what Kubernetes and Yugabyte bring to the table in terms of elasticity. So depending on our read scale requirements or write scale requirements, we can spool up or spool down our command processor and query processor, or our Yugabyte layer or our Kafka layer, and deal with any amount of volume that's necessary. This system is designed to handle, billions of identities, which translates into tens of billions of vaults and hundreds of billions of triples in our triple store. But because of the way we've architected, we can basically dial in the amount of requisite capacity to handle it in a given moment. And I guess that's the end. If I have any questions.